In this class we want to talk about the standard normal distribution. Now this is a way of reducing population distributions down to a standardized form. And when we have a standardized form, we're able to perform various calculations and compare various distributions one with another. We need to get them into a standardized form before we can analyze them. If they're not in a standardized form, it's the true picture of the distribution, but it's not a lot we can do with them statistically. So when we have distributions, we try to get them into standard forms. The standard normal distribution is a special case of the normal distribution. So the normal distribution is a nice bell-shaped curve. It has a mean and it has a standard deviation. On either side of the mean, we can work out the number of standard deviations either side of the mean. But it doesn't go further than that. We need to take that distribution and standardize it. So we're enabled to perform calculations, statistical calculations, which will give us a greater insight into that distribution. So the standard normal distribution is the distribution that occurs when a normal random variable has a mean of 0 and a standard deviation of 1. These are the essential characteristics of the standard normal distribution. The mean must be 0 and a standard deviation 1. So when we think of a normal distribution in the population, for example, the normal distribution perhaps could be on the tolerances in production for a certain item being produced within a company, and the measurements can vary slightly and they may follow a normal distribution. But there's very little we can do with that, because when the machines are retooled, a different normal distribution may emerge with a slightly different mean or a slightly different standard deviation. What we need to do is to be able to perform calculations to see what's the probability of failure above a certain level or success within certain parameters. We need to be able to perform calculations. And to do this, we need the standard normal distribution, which has a mean of 0 and a standard deviation of 1. So we must manipulate our normal distributions so that they have a mean of 0 and standard deviation of 1. Let's look at a sequence here of possible outcomes. Let's say this is x and these are possible outcomes. Then we can, if we use Excel, simply generate the normal figures, the normal distribution figures for this population, for this running from -3 down to 0. And if we enter a command into Excel, which takes the format equals normdist bracket B3, so we'll say B3 is our X column here, B3 comma mean comma standard deviation comma cumulative. Now if we do that, if we enter that, which in this case would look like normdist equals, of course, because it's a formula, equals normdist bracket B3 comma 0 comma 1 comma 0. Now that's the formula we will need in Excel to generate our curve. So we enter that and we have defined our limits. We know what x is, and we have the normal distribution, the normal calculation of the normal distribution on the right. So these are the calculations we have generated. And when you do that, you will get this curve here, which is our normal distribution. What we need to do is to get this into a standard normal distribution. If we, by the way, if we change the standard deviation from 1 to 0.05, you'll see it's much more focused in on the mean. The standard deviation is a lot smaller, so it's not as spread out. The bigger the standard deviation, the more the distribution is spread out. So if we move from 0.05, for example, to 2, it's almost not recognizable as a normal distribution. It's just a curve that's very wide. Compared with 0.05 standard deviation, much focused. 2, much wider. If it goes to 5, it's not really recognizable as a normal distribution at all. It's just a curve. It is a normal distribution. It's just that we can't see the whole picture. Our graph doesn't give us the whole picture, but it is a normal distribution. It's just we'd need to have a very elongated graph to show this. Let's go back to the 1 case. So we've now got our normal dist, which is B3, mean is 0, and standard deviation 1, and it's cumulative. So it's not 1, so it's our standard normal distribution. And if we change that to, let's say, mean 1, it causes the whole curve to shift to the right. So we change the formula from 0, so B3, 0 to B3, 1 on the right hand side. It causes the whole curve to shift over. Now, how do we use this? Well, we use standard score, known as the z-score. Now, the normal random variable of a standard normal distribution is called the standard score, or a z-score. So we have the standard score, the normal random variable of a standard normal distribution. Every normal random variable x can be transformed into a z-score via the following equation. So that's the equation that gives us our z-score. We can see from the equation that z is equal to x minus mu. Mu is the population mean. So it's a particular value minus the mean divided by the standard deviation, sigma. So z is equal to x minus mu divided by sigma. So that's what the symbols mean. X is the normal random variable, and mu is the mean of x. It's the population mean, and sigma is the standard deviation of x. Now, the standard normal distribution table, well, we start with our formula. If we know that the average of a population, mu, so if we know that, and the standard deviation of the population, sigma, then for any given figure we can calculate the z-score. We've got all we need to perform the calculation. With this we can consult the standard normal statistics tables and calculate the probability of that figure occurring. So the picture's got slightly more complicated. We've worked out the z-score, which is our standard score, using our standard normal distribution tables. But we need to consult these standard normal statistics tables in order to work out the probabilities of a certain figure, the probability of a certain figure being above or below a certain level, and so on. So we need to be able to consult the standard normal statistics tables. We must have these available if we're going to do this calculation. A standard normal distribution table shows a cumulative probability associated with a particular z-score. Now, to find the cumulative probability of a z-score equal to minus 1.43, cross-reference the row of the table containing minus 1.3 with the column containing 0.01. The table shows the probability of a standard normal random variable will be less than minus 1.43 is that, and the is 0.0764, and is the probability is z is less than minus 1.43 is equal to 0.764. So we do this with reference to the tables. It's probably easier if we look at a table. There's the table. What we're looking for here is 0.43. So we look at minus 1.4, look at 0.03 on the top, and where the two intersect we get 0.0764. So that is a probability figure. That tells us the probability that a random variable will be less than 1.34 is 0.0764. Suppose we want to know the probability that a z-score will be greater than 1.34. From the table we find that the probability z is less than 1.43 is, we've just calculated, 0.0764. Therefore, the probability of it being greater is just the probability of 1, which is absolute certainty, minus what we've just calculated. So the probability of it being greater must be 0.9236. If it's less, if the probability is less than 1.43, it's 0.0764. So therefore, the probability of it being greater than 1.43 must be 0.9236. Find the probability that A is less than Z, which is less than B. Now the probability that a standard normal random variable lies between two values is also easy to find. The probability A is less than Z is less than B is equal to the probability that Z is less than B minus the probability that Z is less than A. If you just break up that first statement, you will see that is true. It must be true. For example, suppose we want to know the probability that a z-score will be greater than minus 1.3 and less than 1.22. Well, the probability of minus 0.3 is 0.0968, indicated in green on the table, and the probability of it being less than minus 1.22 is given in the table as 0.1112. So once we've got those two figures, we can perform the calculation. From the table above, we find that the probability of z is less than minus 1.3 is 0.968, and the probability of z being less than minus 1.22 is equal to 0.1113. Therefore, the probability of z lying between those two must be one minus the other, which is equal to 0.144. So the standard normal distribution is extremely useful. And sorry, let's go back just to where we were. It's extremely useful in enabling us to do these type of calculations. Take another example. Find the probability of A is less than Z less than B. Now we use the standard normal random variable lies between the two values, so it's easy to find. That's the sequence, and it's exactly the same as we have just done. For example, suppose we want to know the probability that a z-score will be greater than minus 1.4 and less than 1.2. From the tables, we find that pz is less than minus 1.2, which is equal to 0.1151, and the probability that z is less than minus 1.4 is 0.0808. Therefore, the probability that z lies between the two must be that it is the difference between the two. It's z is less than minus 1.2 minus the probability that z is less than minus 1.4, which is just 0.343. Suppose David is a student in a year group of 152 students. Let's say he's 61 centimeters tall. That average height of students in the group is 59 centimeters, and the standard distribution of their heights is 4.3 centimeters. What proportion of students are taller than David? And we have to assume that the test scores are normally distributed. So here's the situation. David's in a group of students, 152 students. He's 61 centimeters tall. That's how tall he is. And the group, the height of the group is 59 centimeters, and the standard deviation of their height is 4.3 centimeters. So, what proportion of students are taller than David? Well, if we imagine the distribution to be like this, we know that the average is 59 centimeters, so we draw 59 as the average. That's the central point. That's the point of the axis on the distribution. So it's the axis of symmetry. If you fold the curve over on 59, it'll fall upon itself. We know that David is 61 centimeters tall, and we know that the average, the standard deviation, sorry, the standard distribution is 4.3 centimeters. So the solution: transform David's height into z-scores. Well, z is equal to x minus mu over delta, which is equal to David's height is 61 centimeters. Take away the average, which is 59, and divide by the standard deviation, which is 4.3. So David's z-score is 0.465. Now the standard normal tables, well, if we have access to the standard normal tables, and you can get them online quite easily, just many institutions give access to those tables. Just do a search on standard normal tables and there's plenty to pick from. So we do a test there, and we find that pz is less than 0.465 is equal to 0.6664. Therefore, the probability of z being greater than 0.465 is equal to 1 minus that figure, which is equal to 1 minus 0.6664, which is equal to 0.3336. Thus, we estimate that 33% of the students were taller than David. You can see it's a very powerful technique for working out probabilities. what proportion of the class were taller than David, or we can do all sorts of calculations using this. We are making assumptions that the distribution is normally distributed. It's a standard normal distribution. And what it's doing is it's transforming the distribution into a distribution with mean 0 and standard deviation 1. And it does that using the formula x minus mu divided by delta. X being the variable from the distribution, mu the average of the population, divided by the standard deviation of the population. If you divide by the standard deviation, you're going to get a standard deviation of 1. You've divided by the number itself. If you divide any number by itself, you'll get 1. So we're getting a standard normal distribution by using the formula, and we're able to solve problems such as this one. If we take this particular problem, just having a look at it here, David is a student, a year group, 152 students. He's 61 centimeters tall. The average height of the students is 51 centimeters. So we're changing it now. And the standard distribution of their heights is 3.3 centimeters. What proportion of students are taller than David? Assume that the test scores are normally distributed. That's the big assumption, of course. We have to assume that the test scores are normally distributed. If they're skewed in some way, if they're not following the bell-shaped curve, then of course these calculations are not valid. But we'll assume that they are. Now the solution is to transform David's height into a z-score. And we do that by z is equal to x minus mu over delta. We had it before. In this case, is equal to 61 minus 51. 61, that's David's height. Subtract the average for the population, which is 51, divided by the population standard deviation, 3.3, which gives us our standard normal figures. In this case, the z would be 3.03. Now use the standard normal tables. The probability that z is less than 3.03 is equal to 0.9988. Therefore, the probability that z is greater than 3.03 is equal to 1 minus the probability that it's less than that number, which is equal to 1 minus 0.9988, which is equal to 0.0012. Thus, we estimate that 0.12% of the students were taller than David, which makes absolute sense. If you look at the question posed, David is significantly taller. He's 61 centimeters, whereas the rest, the average, is 51. And the standard deviation is 3.3. So the chances of students being taller than David is very, very small, which is exactly what we calculate. In this case, we calculate it's 0.12%. So it's very, very small probability that any students will be taller than David. David's a student in a year group of 152 students. He's 61 centimeters tall. The average height of students are 61 centimeters. Now they're the same height as David. And the standard distribution of their heights is 3 centimeters. What proportion of students are taller than David? We have to assume again the test scores are normally distributed. Now in this case we just changed the figures to make the average of the students is 61 and David is 61. Now what proportion will be taller than David? Well, transform David's height into z-scores. In this case, it's x minus mu over delta, which is 61 minus 61 divided by 3, which is equal to 0. The numerator is 0, the denominator is 3, the answer is 0. Now use the standard normal tables. The probability of z being less than 0 is 0.5. Therefore, the probability of z is greater than 0 is equal to 1 minus the probability it's less than 0, which is 1 minus 0.5, which is equal to 0.5. Thus, we estimate that 50% of the students were taller than David, which makes absolute sense. They started at 61 centimeters each. Half of them will be taller, half of them will be less than David. Now, to many of you, this may seem a confusing class, complicated and confusing. For a start, we take a normal distribution and then we transform it into a standard normal distribution. In other words, we force the mean to be 0 and the standard deviation to be 1. And when we've got it in that setting, we can use it to make these probability calculations. Of course, we need the distribution to be normally distributed. That's the overriding assumption of all of this. But once you've worked your way across the examples I've given you here, you'll find it's quite straightforward. All we've got to do is to remember the formula and transform the real figures into these standardized figures, and then use the standard normal tables to work out the probabilities. So it's a question really of just working over it several times and coming to terms with the fact that you're not working with a normal distribution, you've transformed the normal distribution into the standard normal distribution. You've moved it from its own mean and its own standard deviation into one which has a mean of 0 and a standard deviation of 1. Once you've got it into that format, we can use the standard normal tables. And then we're able to work out probabilities. And that's the whole purpose of this exercise. As I said, you may find it confusing and a bit difficult to get your head around at the start, but if you go over it a few times and think about it, the normal distribution is aesthetically very pleasing, but it's not very useful to us because there's an infinite number of means possible, perhaps, and an infinite number of standard deviations. So there's nothing we can do with that except say, oh look, we've got a standard normal distribution and it looks good. But we can't do any calculations with it. What we need to do is to get it into a standard normal situation where we can do probability calculations. And the way we do that is just by applying the Z formula. Take away the mean of the population from each of the values. Well, that reduces it down to mean 0. And divide by sigma, divide by the standard deviation, which gives us a standard deviation of 1. So we've reduced our normal distribution into the standard format. And then you can imagine all normal distributions being forced into that standard normal distribution, which enables us to do these calculations. Worth thinking about. It's a topic that will be dealt with in other videos. It'll be dealt with perhaps more gently in other videos. This is just meant to show you why it is we transform the normal distributions into standard normal distributions and the type of calculations we can get when we do so. But that's all we're going to deal with here, so let's leave it at that and say thank you for watching.